23. All right, on 23, we have a right triangle. And we have 13 hypotenuse here. It says that in the right triangle, the theta is increasing at a constant rate of 2 radians per minute. And remember, we're going to write that as a derivative. 2 radians per minute. As we see that rate, expect that to be the derivative here. And it says that the in units per minute, at what rate is x increasing when x is equal to 12? So notice that we're keeping the hypotenuse constant here. Okay. I believe it says 13, right? Yeah. Okay. And we ultimately need an expression here that will relate our theta and our x. Okay. And so our theta and our x to be related by tangent. Theta equals x over 13. Right. And if we differentiate with respect to time here, we'll get secant squared theta d theta dt. And over here we'll get 1/13 dx dt. Keeping in mind that dx dt is what we're looking for here. We want the change in x with respect to time. All right. And we know that we want this to be 12, remember, right? So that means that at the instant we need to find theta. So again, we know tangent of theta to be 12/13. So theta would be the tangent inverse of 12/13 at that point in question. Okay. All right. And so ultimately we can calculate that. This is a non-calculator, right? Yeah. So we know d theta dt is the 2, so we can put that in there. Okay. So we ultimately need to figure out an expression for secant. Keeping in mind that if tangent theta is 12/13, put that in there now. Normally the x at the start. We know that this is a 5, 12, 13 right triangle. That's how Pythagorean triple 5, 12, and 13. And so the question is, can we come up with an expression for secant? Well, remember secant is the reciprocal of cosine, and if cosine is adjacent over hypotenuse, then wouldn't secant be hypotenuse over adjacent, 13/5? And so if we do 13/5 squared, we'd get 169/25 over here on the side. So again, remember, if tangent theta in this picture is 12/13, then secant's going to be hypotenuse, just like this one's opposite over adjacent. Secant would be hypotenuse over adjacent instead of opposite over adjacent. So again, we're squaring it, secant squared. So we get that. And then ultimately we'd multiply both sides by, divide by 1/13 or multiply by 13. Okay. And we'd wind up with, yeah, that's not going to wind up right, I don't think. None of those reduced. We have 26. And none of those are going to be whole numbers. Let's see. Let's see what. Oh, you dummy. Yeah, you're right. Let's try that again. Say, something's not right. Let's try that again. Ultimately, again, that being x at the beginning, it should be sine. So, with that, if I know that my sine, that means that my derivative this time is going to be cosine theta, d theta dt. That'll make the numbers a lot easier. And then 1/13 dx dt over here. Still looking for dx dt. This is still 2. In this case, again, if I still have 5, 12, it's going to be, cosine is going to be adjacent over hypotenuse. So it's going to be 5/13. And once I multiply by 13, that's going to give me dx dt over here. So that'll be gone if we multiply by 13. 13s will cancel out and be left with 10. There we go. See, somehow that wasn't working out correctly. So 10 matches up with D. Does that sound? Yep. Good. All right. So again, the relationship that we want to look at is the fact that theta and x and 13 are related. Okay. So opposite over hypotenuse, not opposite over adjacent. So not tangent. All right. Questions on that one? What else? 1 through 28. Matt? 24. Let's see. On 24, we have says the Taylor series for cosine about x equals 0 is given. And it says if h is a function such that h prime is cosine of x cubed, then the coefficient of x to the 7th in the Taylor series for x about x equals 0 is what? Right? So we know that in general that the cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial and so on. Okay. And we know that this h prime function says h is a function such that the derivative is cosine of x cubed. Right? All right. So if that's the case, then our if we were to take our keep in mind that this is just our cosine function, so whatever we want to call it, if we want to call it f of x or whatever, so we'll call that f of x. Okay. If we were to find the derivative of it, the derivative of f prime, if you will, if we were to differentiate these, we would get 0 here. We get 2x to the 1 over 2 factorial, which will simplify in a minute. Then we get 4x to the 3 over 4 factorial. And then the next one here, remember this was minus x to the 6th over 6 factorial. And then x to the 8th over 8 factorial, and so on. So if we were to differentiate the cosine function itself, and again we'll simplify in a minute, but ultimately we get 6x to the 5th over 6 factorial, and then 8x to the 7th over 8 factorial. So if we were to differentiate here, this would be our derivative of cosine situation. So we'd ultimately have x, and then over here we'd have x cubed over, and then the 4 and the 4 would cancel out, we'd be left with 3 factorial. So 3 times 2 times 1 would be 6 here. And the 6's would cancel out, we'd get 120 here, x to the 5th here. 8's would cancel out, we get x to the 7th. 7 factorial would be 720 times 7. Do that math or not? I need to. Actually, I think they still have it in 7 factorial notation, don't they? So it's ultimately 7 factorial. Let's leave it as such. Okay. All right. So ultimately, if this is our f prime for cosine, because remember again, this is our Taylor series for cosine. Okay. This would be the derivative of cosine. Yep, you're right. Yeah. So this one was negative. Negative, and yeah, these are all negatives, these ones. Okay. All right. So once again, if this represents the derivative of cosine, because again this one being representing cosine, this one represents the derivative of cosine. The question is, how does that factor into if I have this h prime function, if I have it as cosine x cubed? Okay. If I want the cosine x cubed function, remember what this really represents here is ultimately represents negative sign, doesn't it? Because ultimately we get, again, if we have our if this represents the derivative of cosine, the derivative of cosine is negative sign. Okay. So, with that said, that really isn't so much related to this. What if we did, if we had our h prime function, okay, if we wanted to find an antiderivative for cosine of x cubed, would that be an option for us? And if so, what would it be like? And if we have cosine of x cubed here, the argument being x cubed, we'd have, if we tried to use substitution, our derivative, our u would be 3x our du would be 3x squared, which ultimately there wouldn't be a dx 3x squared to get rid of. So if we were to put our cosine, or x cubed in here, and knowing how we can transform our cosine function, keep in mind that if we, just knowing that this is cosine, if we wanted to get a Taylor series for h prime, couldn't we just take the x cubed and put it in the original? Because remember, whether a derivative is a function one way or another. True? Okay. When we take a derivative of something, we get another function. True? So ultimately, couldn't this h prime be represented by this, but with an x cubed plugged in there? So let's try that. So if we plugged an x cubed into this, we'd have x to the 5th over 2 factorial minus x to the x to the 6th, I should say. Sorry. We'd have an x to the 6th. In there, we'd have x to the 12th over 4 factorial. We'd have an x to the 18th over 6 factorial. We'd have an x to the 24th over 8 factorial. Okay. And so on. Again, we could go as many of those as we need to go. Okay. So bottom line is, since cosine itself is this, okay, this function, whether we call it h prime or smiley face prime, or smiley face at all, anything, whatever we wanted to call it, doesn't really matter what the name of it is. Okay, if I have cosine x cubed, then this could be represented by this, with the x cubed in there. True? So it doesn't really matter whether it's a derivative or a function or otherwise, we can still represent this h prime by what we have here. Now, the key question though is, how do we find the coefficient of the x to the 7th term in h? Well, if we have a representative for h prime here, how can we get back to h? We just anti-differentiate term by term. So we get an x here, right? And in this one we get a minus x to the 7th over 7 times 2 factorial. And really we can stop at this point because the rest of them are, all we need is the x to the 7th term. True? And so ultimately, again, what is the x to the 7th term's coefficient? It would be negative 1/14, should be letter A. So again, I'll take you a little bit of a roundabout way here in terms of, if we knew the cosine and somehow we had a derivative here, I guess the key element here is to just recognize that if we have a known Taylor series, okay, that we can find a new Taylor series by just replacing the x with whatever the argument is, the new argument. Okay? And whether that's a derivative or not is irrelevant, isn't it? Okay? So ultimately, if I just had this, whatever I called it, whether it was a function or a derivative or a second derivative or whatever, okay, we could still represent this expression, okay, with this, with an x cubed plugged in there. Okay? And ultimately that gives us an expression for h prime in this case. And once we have an expression for h prime, then we can find h. All right, what else? Oh. 27. And 27 looks like a integration by parts problem, since we can't u substitute here. Neither one of those letting be u would give us a good du. So let's try letting our u be 2x and our dv being cosine x. That means our du would be 2 dx. Our v would be sine x. Right? And knowing our integration by parts is 2x sine x uv minus v du. V du would be sine, would be 2 sine actually, 2 sine dx. We go v du. And sine x, that is. And at that point, we'd have 2x sine x. Take the 2 out, anti-differentiate sine x, we'd get negative cosine x. Plus c. Alright, and so we'd ultimately get 2x sine x plus 2 cosine x plus c. And it looks like that would be choice E. see how that's. They have D as the answer here, but I'm not sure how that can be D. So if we go 2x here, cosine, antiderivative cosine of sine. That might have been one of those free ones. I told you I gave you, I think, 2 or 3 free ones. Okay, so if we take a 2 out of there, sine x dx. And even multiplying that in there, still just C. That's minus. Yeah, that one should be E. Unless I'm missing something, but I think we're good.